Very grateful to those of you who are participating in this, to our friends, our alumni, basically the family for Lamont. It's particularly important as we approach Columbia's annual Giving Day that we recognize our donors. They've been very important to us in the last year, and as we navigate our way through the current environment, continued support is very important to us, and we'll get to that at the end of the seminar here as well. But today we're going to be talking about weather and climate. There's an old aphorism, some of people actually attribute it to Mark Twain, which is that climate is what you expect and weather is what you get. That's actually not Mark Twain. Mark Twain wrote about something different. That particular formulation of the aphorism is due to Robert Heinlein, as I noted, as I found out, in his book, Time Enough for Love, which for those of you who are Heinlein fans, it's a really weird book. But anyway, the notion here is that climate is long-term, on the average is what we expect to happen, whereas weather is something that we actually get on a day-to-day basis. But that distinction actually blurs a little bit when we start thinking about the interaction between weather and climate, or in fact, what weather is going to look like as the climate itself changes. And that's what we're going to be discussing today. I'm really happy to see Michela Biasutti, who is a Lamont Research Professor, and Chia-Ying, who is a Lamont Associate Research Professor, both members of Lamont senior staff, who will be talking with us this morning. So as before, we'll begin with a couple of lightning talks, and then we'll have the Q&A session. So please put your questions into the chat or the Q&A. We're monitoring both, and I'll take it from there. But right now, I'm going to turn to Michela, and off you go, Michela. You're muted.
Unmute. Here we go. So thanks everybody for showing up. What I want to talk to you today about is, here we go. Two stories of extreme rainfall that are happening in monsoon regions, and I'm gonna focus on places where we have a large number of people living. And so these stories have real consequences for a huge number of human beings. And so the two places are West Africa and South Asia. And here you see the rainfall for summer in blue. And so you see that during the Northern Hemisphere summer, this is what the rainy season, both over North Africa and over Asia more generally. And the first story is about Pakistan. So you might remember the news from 2022. For a lot of the monsoon season, Pakistan looked completely inundated. This was a huge event, more than 1,300 people dead, a huge swath of agricultural land, especially in the south, destroyed, 33 million people displaced by the floods. And when you look at what happened that summer, it was really an incredible amount of precipitation. So here is, we're looking at data from 1980 to 2000 and again 2022. And this amount of rainfall, we're not quite sure depending on the data set, but for sure more than 5 standard deviations away from the mean, meaning completely unprecedented for the record from 1980, but of course, from the memory of people there, incredible even going back in time farther down. So how did this happen? It was really just a handful of storms. So let's look at what happens during the South Asian monsoon. Storms usually are born in this area, in the Bay of Bengal, where you see these orange lines. And then they move on to continental India, and usually they die off over central India. Very few make it across. And in 2022, a few did. And those are the storms that created this flooding. So we wanted to understand what exactly happened and why. So we started looking at these storms more in detail. These are called typically low pressure systems, and when they're stronger, they become monsoon depressions. But what they look like is kind of small, misshaped tropical cyclones. So they're rotating system, but they're not as symmetric as a typical hurricane. And they're generated in this area where we have strong differences in both wind and humidity as going from the ocean towards land. So a student here at Lamont started tracking these systems in a lot of data sets and looked into what happened in the 2022 season. So what we show in this figure here is that during that time, the storms, instead of sticking to this northern part of the domain, they were tracking farther south. And not only that, but they were expanding into these areas where they usually don't get. So in blue here, the blue dots indicate very heavy rainfall anomalies. And again, the green bluish background color indicate where the storms were tracking. So the number of storms was not exceptional for the season, but these were intense storms, and they made it all the way to Pakistan and stayed there for much larger number of days than usual. So we really wanted to understand what changed these kind of long tracks. So we looked at the large scale changes. So again, we're talking about the connection between the weather event and the large scale climate and how it changed. So for the season, and we saw this large scale pattern of more monsoon wind bringing more moisture. So the arrows here tell you where the wind was going, and the green indicates that it was bringing more moisture to the area. And so not only this is what happening in 2022, but when we looked at the trends in this moisture supply, we saw that there was a clear indication that this was not an isolated event. It was the culmination of a trend in increased moisture supply to the region. And this is also in line with what climate models are telling us we can expect for the future. So we expect when we look at scenarios simulation in which we increase CO2 either quite a bit or incredibly lots, we see this increase in trend in the expectation of seeing more and more of these storms reaching Pakistan. Okay, so that's my first story. And I want to talk about another story about West Africa. This is a place that is very dear to me because I've worked for many, many years on understanding a very different but connected phenomenon, which was the drought. If you're of a certain age, you might remember the drought that hit Ethiopia and the Sahel in 1984-85. That's a time when the rainfall was incredibly low in this region. And since then, we've seen a recovery of the rainfall, but we've also seen, and people on the ground have complained about the fact that rainfall has become more extreme. So more variable and more extreme. So here is an example also from 2022 of floodings in Nigeria, but this is just one aspect of, again, a trend where the contribution of extreme rainfall to the annual mean has been going up and up and up quite substantially, so that now it makes up more than a third of the annual rainfall comes as extremes, the kind of events that cause this flooding. Where does this come from? Again, if there's a trend like that, something in the large scale is happening to create this trend. And so again, though, you need to follow the storms. And the storms that cause rainfall in the Sahel look a little bit like this. They're called mesoscale convective systems. And you can track them from high-resolution satellite data. This is work done in collaboration with a student, in collaboration with colleagues in Europe. And so we could track them as they move across year by year by year. And what did we find was happening? Well, interestingly, at the beginning of the trend, as we were coming out of the drought, we see this measure of the cloudiness of the storm, which basically you can think of as the number of storms. We see that having a very strong upward trend, more and more storms coming into forming and coming into the region. Here we go. As for the second part of the record, though, instead of seeing this number of systems increasing dramatically, what we see is kind of like not much of a change in the number of storms. And instead, we saw that the amount of rainfall that was coming per storm, that was getting to be stronger. So when we talk about the future, we kind of want to distinguish between these two possibilities, more storms or more intense storms, or maybe more. So in general, we know from theory, we have a very strong expectation that a warming world will bring more extreme rainfall. When we think in terms of, globally or over a very large, like continental area, there is no doubt that we will experience more extreme rainfall. What the research is trying to do, though, is go beyond this general truth, right? And so if we want to have better prediction of the distribution of storms, right? Well, will they track? Will they switch from one place in India to another? Will they reach further afield, right? That's what the story about Pakistan told us, that we need to know, where the storms will go. And then the story from West Africa tells us that we also need to understand exactly how many will they be. Will they increase in number, or will they maybe stay the same and just their intensity will grow? We don't yet know. This is computationally really hard work. It takes huge data sets, a very high temporal and spatial resolution to track these systems. And it takes the next generation of climate models to really resolve these smaller scale tropical storms. So, of course, next generation means high resolution, high computational cost. And it's hard work. And that's why we could only now basically start doing this. And so with your help, Lamont can stay at the forefront of this important work. And I hope you find it as fascinating as I do. So I want to thank you.
Thanks, Michela. Again, let me remind everyone, please put your questions into the chat or the Q&A, the tabs at the bottom of your screen. This is a webinar format, not a typical Zoom format, so please put your in, and I'll ask the questions as we go forward. So thank you, Michela, for that. And now we're going to turn to Chia-Ying, who will give us also a short presentation. Chia-Ying.
Sure. Let me share my screen first. All right. So, first of all, so today I want to talk about also equivalent climate, focus on the risk of tropical cyclone or hurricane, as we call it here in United States, for North Atlantic and the Eastern Pacific. So I believe many people have learned from the news or have already heard that as the climate warms, a landfall hurricane will causing more damage due to more intense wind, heavier rain, Michela just mentioned, and the more widespread storm surge, which is partially also due to the sea level rising. And the image I'm showing you here is actually, you can see a slightly increasing trend of number of billion-dollar tropical cyclone events in the yellow and the number of economic causes by those storms. And we see a weak trend. While the statement and the trend we see is true because it is referred to the individual damage, the damage that made from individual hurricanes that made landfall. our recent work has actually pointed out that future hurricane risk, or let's focus on our homeland, United States hurricane risk, is actually uncertain. And there are many reasons behind such uncertainties, and I'm going to discuss from two directions. One is from global perspective. Our research has found that the projected future tropical cyclone frequency, or you can think as annual number of the tropical cyclones globally, is actually uncertain. How so? So from the past several decades, we have learned that some conditions, some climate conditions, or some environmental conditions are good for tropical cyclone. Like a warm ocean is good, dry atmosphere is bad, strong wind at different levels is bad as well. So by combining those information, we can already estimate the number of tropical cyclone, annual number of tropical cyclone, more or less close to observations and show you here. And however, depends on how we combine those information. When we get the information from global model and using the same way we formulate the relationship between tropical cyclone and the background climate, we get different projections. One method can lead to the increasing projection, and the other method can lead to decreasing projections. And because we are so far to date, there are no theory explain the number or annual number of global tropical cyclones. There's also no theory can actually describe in the tropical cyclone genesis. We are not able to distinguish, or we are not able to determine which direction we should trust more. And the projection I'm showing you here is downscaled from a Columbia hazard model that developed in-house at Lamont, found using global model output. But the same diversity, like divergence projections, you can find using other tools. So this is one from global perspective. More stone or less stones globally. Now, at the regional, a bunch of Lamont scientists led by Richard Seeger has been in the past several years discuss about how the projected trend in the equatorial tropical Pacific under the climate global warming scenario is quite different from the past observations, despite our climate has been warmed. And their argument is that the differences is actually a systematic model bias in the tropical Pacific sea surface temperature. So the differences are that, as I show here, projected trend of sea surface temperature showing a more warming in the equatorial region relatively to the subtropical area. We call it the El Nino-like trend, while observed shows more cooling or relative cooling compared to the subtropical area. We call it La Nina-like trend. So what does that matters when we talk about the U.S. hurricanes? Because we have learned from El Nino or La Nina influence, we know that during El Nino events, there will be less hurricane in the North Atlantic, and therefore we expect less landfall. And there is a reverse during the La Nina year. So this understanding actually showed up when we look at the climate projected hurricane trend, which I show you here. Blue means less, red means more. And you can see in the Atlantic, climate model project decreasing, while our observational in the past 30 decades shows an increase. So the question we ask ourselves is, how can we do a risk assessment if we don't know the possible change of directions, like the example I show you for the frequency, or if all global models are biased, with no model that look like reality, as I show you the situation of tropical Pacific, or you can see a schematic of diagram I show you here, all the model in one direction while reality going to the other direction. So the approach we try to do is go through so-called storyline approach, meaning that we can follow one of the direction and try to look at the possible outcome of risk, and therefore we have a full range cover of possible, like a full coverage of possible range of future risk projection. And several ways you can do storyline in several approach. There are several ways to do the storyline. And I'm going to show you one of the work done by a postdoc at Lamont, which we decide to do is, if the model has bias, which I show you here, this is referred to the tropical Pacific example I'm showing you here. So here shows the model bias. Blue means model is too cold. Red means model is too warm. If model has bias itself, we can do the bias correction by removing it and hopefully to generate projections that are more in line with observations. And the result is it does more in line with observation. So before corrections, simulation is here. After correction, simulation is in the middle. Don't trick by your eyes. They look quite similar, but if you use one minus the other, you will see the results is indeed bring the model simulation more towards La Nina-like pattern and more towards the observation. And then we can continue, go into the future and look at the hurricane trend here now. And again, I want to bring your attention to close to the North Atlantic region here. You can see before correction, the model project overall decreasing. After correction, it is more or less non-change. And what the change largely is in the basin like Western Pacific, even the sign is changing. So the work I'm showing you here is actually talking about how are we going to characterize uncertainties when we try to quantify, how are we going to quantify the uncertainties in the climate projections of extremes, and especially for the case that is difficult to quantify it, because the model ensemble doesn't actually capture them, and as Michela has been discussed, we rely on global model to tell us what are the future. And the problem is generic. Even though I talk about TC risk, talk about tropical Pacific that has specific issues, but it is generic questions. And we want to be able to solve it or to study it for scientific curiosity and also for pragmatic perspective, because estimate the risk of extremes is what actually be used for climate mitigation and adaptation. So I think I'm going to stop here. Thank you.
Okay, thank you, Chia-Ying. That's very good. Again, please put your questions into the chat or the Q&A tab. We're monitoring both, and I'll get to them. We already have a few. But I want to start off with a bit of a general discussion to both Michela and Chia-Ying, having to do with this notion of prediction, forecasting, the use of statistics versus the use of the models. And in your careers, how has that been navigated? Essentially, when we think about prediction and forecasting, often we think about past statistics, statistical models, probabilistic models. And of course, a lot of the seasonal forecasts have been probabilistic, particularly during the US hurricane system. But now we've got computational strengths. In your careers, have you seen a shift between the statistical approach to the modeling approach? And how do you think that's coming together? Maybe Chia-Ying, you can start off.
Yes, so I think for hurricanes, definitely a clear shift from statistic. So even right now, there are still a model that called statistic hurricane intensity prediction system that is used by National Hurricane Center. It's developed in 1980s. And that's when the time that when we try to predict intensity, the best model is from statistic, which is kind of, again, similar to what I said, connect the non-environmental condition to the intensity change and trend by the pace data. But in the past, I think 5 to 10 years, the dynamic model, the real model that simulates weather organic based on law of physics, shows that they are value and they are already kind of better than the statistic model, especially when for the extreme cases. The problem with the statistic projection is always statistic projections try to look at the mean. So when we talk about extreme, those are 5 standard deviation, like example Michela used. The statistic model will not be able to capture, even if their skill are good overall. So in hurricane predictions, weather predictions, it definitely has already moved from statistic to the dynamic model, even though the statistic model is continue running. And when we talk about seasonal, they are combined both. Yeah.
This goes back to our initial aphorism about weather and climate. In some sense, volatility is weather,
Yes.
right? And the mean is climate in some way. And we've always had difficulty with dealing with extremes in some way. Michela, on a related tack, we often think about the day-to-day weather. We listen to the weather reports every day, of course. Then the seasonal predictions, I go back to the Kane and Ziebiak sort of, and so sort of seasonal notion, monsoons are seasonal, and then there is climate. In your mind, is there a distinction between weather, day-to-day, seasonal, and climate? Are they all one and the same, or are they just different versions of the same thinking about the Earth's system, weather system, atmospheric system, I should say,
Well, so the first thing I want to say is that we don't think of climate as just the mean of the weather. We think of climate as the sum of all the statistics of the weather. So what is the mean, but also how variable, how volatile, as you were saying, that the day-to-day is within that season, right? So that's the standard deviation. Oh, how skewed it is. Do we have more of one kind of events than the opposite? So climate can be described with a rich set of statistics, not just the mean. But and that's what makes this interesting back and forth between weather and climate in our research. But the important thing I would say is that, for prediction, the weather is obviously something for which you start from initial conditions and how the large scale is going to evolve slowly, and then you have these faster things happening that are determined by what's happening today, right? When we think about predicting the climate as a seasonal event, or even farther when we think about projection for climate change, that's all about how we're changing the system from the outside and what are the boundary conditions for that prediction. And so the one thing that is always important to remind people of when we talk about what's going to happen in the next 20, 40 years is always that it's not something that is just going to happen to us like the weather, right? This is something where we are active players because we are modifying the boundary condition in which the weather happens, right? We are changing the amount of CO2 in the atmosphere. We are changing the amount of other pollutants in the atmosphere. So, it's not something that happens to us anymore, is it?
We're part of the geological forces shaping the planet. That's why we call it the Anthropocene these days. That's one way to think about it. But we're on human time scale, so we worry about weather, we're worrying about seasons, and now we're worrying about climate effects, weather, and seasons. Turning to a couple of the questions in the webinar, I see Richard Wurzel. By the way, those of you who know the history of Lamont know that Morris Ewing and Joe Wurzel were the founders of the Lamont Observatory, and I'm pleased to see Richard here. And Richard, I guess you missed my earlier comments that the quote that climate is what we expect, but weather is what we get is actually due to Robert Heinlein in that particular construction in a very weird way. We can get offline on that one. Anyway, Richard and a few others have asked about the notion of modeling. And again, let's go to Chia-Ying Li about this, the complexity of modeling. How is that being addressed? There are questions related to whether you could use other types of programming approaches as opposed to, say, deterministic solutions of differential equations, say, genetic programming or evolutionary algorithms, something that I did about 20 years ago, or AI for that matter. So beginning with Chia-Ying, let's talk about where you see modeling going in the context of let's take the AI question, and then Michela, we can turn to you similarly. So Chia-Ying.
So, okay, so let me rephrase the question. So you are asking me how I see AI play a role
Let's take
in the
specifically.
hurricane prediction or projection.
Yeah, specifically. Yeah.
So I think first of all, AI definitely is going to play a very important roles in improving, hopefully, improving our predictions. And one of the reason, and one of the reason is just because it can generate a way much more larger ensemble cheaply, and then give us a higher, like certain of the statistics that we know. But on top of that is because when we do the predictions, especially using numeric model, we are always kind of limited by how fine resolution we can go, right? But when we talk about weather prediction, we actually want to know the weather coming out in front of our home. And those kind of fine resolution, the numeric models or even hurricane model, regional hurricane model is not able to resolve. But this is the area I personally think AI can actually do, kind of downscale from the weather prediction model to a very localized prediction. And then that can give the information that can be used by a very small scale. And in terms of climate projection with AI, I think there's actually, we have to think about what AI is training on. So AI is trained on global model that have hard time to simulate hurricane accurately, or AI is trained on the global climate model that has a systematic bias. But if those model, the training data sets is imperfect, then you go to the training and your output data will be imperfect. In fact, one of our colleagues has tested that try to train the AI model without giving any category 5 hurricanes, then the model itself did not produce any category 5 hurricane. But if they switch the training data by adding category 5 hurricane artificially, then you can generate that. So I think to sum up what I say is, I believe AI will have large impact in our weather prediction, especially localized micro weather, like a micro prediction in the localized area. And climate projection, I think AI will also have impact, but we have to be careful, cautious about what we put in. Yeah.
Yeah, Michela, in addressing, a similar question as well. I know you have, and I have certainly, grown up in the era of computational math, basically solving differential equations on a computer as opposed to something more esoteric. But in particular, data plays such an important role in validating the models, whether you're using AI inference or validating your approach to the differential equations. What's the role of data these days? Obviously, we're going to be worried about data collection and so on, but talk a little bit about how data enters into the modeling process.
So the models of the ocean and atmosphere that we're using for climate projections, as Chia-Ying was saying, they can only go to a certain scale, right? And meaning it's like taking a picture where you have a certain number of pixels available to you. And but for the climate, you need to be able to simulate things as small as how much ice form in a cloud as opposed to liquid water, because that's going to change how much of the sunshine that cloud reflects, for example. So we'll never get to those kind of scales. So even though we have the differential equation for the large scale of motion, there are some processes in our model that will not be solved in that way. And data can come, and AI can come into this interface of the very small scale with the scales of motion that we can, in fact, understand via differential equation. So there are efforts happening right now of taking the huge amount of data streaming from satellite, for example, about clouds, and change our understanding of how we combine this very fine scale with the large scale. So that's a lot of data that we have as long as the US keeps those satellites up in the sky. And it's being used as we speak. The other thing that I want to, as we are thinking about models that need to be able to reproduce not just things that we have seen and observed in the last few decades, but we're thinking about, trying to understand what's going to happen in a future that is uncharted, right? Where the training data, again, the data that we observe specifically, directly is not going to be enough. I'm thinking that there are some very creative way of using the paleo record that might, we've used the paleo record to figure out when our models, our current models, are right or wrong in many ways. And I think they're going to be a really important test bed for as these new class of models come online. And of course, it's something dear to our history as the Lamont Observatory.
Yeah, as a working on the solid earth side of things, understanding paleo is always important to actually try to figure things out that way. Um, but Chia-Ying, are there good indicators of paleo storms? I mean, how do you figure out what happened in terms of volatility, say, in paleoclimate?
I think so. They are using the sediment records for the coastal floodings because when there is a huge stone surge, that's where you can get the record, and that's one of some scientists has been looking into how to connect those paleoclimate data into for assessing hurricane risk even. And another possibility is to look at the precipitation influence on the trees, but I think that has to be very specific type of trees that can have this kind of records. And I believe in part of US, you will have this kind of data. Other one is about the heavy precipitations, because if you have heavy inland precipitation, then I think they will leave some records. So yes, paleoclimate data on the hurricane and how extreme it is connect to the temperature back there is one of area that actively being studied. Yeah.
Okay, let's turn a little bit to some of the uses of the work that both of you are doing. And again, Chia-Ying, and we'll turn to Michela shortly, but you introduced the Columbia hazard model that you worked on, the TC model, tropical cyclone model as well. And the impetus for this, as I understand it, was that the real metric for making socioeconomic decisions, even personal decisions, is risk. Define for us what, in your mind, when you try to quantify what risk means, what is risk in this context?
Well, I think risk, so the definition of risk usually contains three components. One is the probability, a chance of event to happen to you or to an area you are interested in. The second one is what's on the way. What do you have on the way of that event? And the third is how resistant whatever property you have on the way is. So that co-vulnerability, exposure and vulnerability. So the risk we are thinking of how resilient we are at a location where we are facing the chance of extreme events coming towards us. And that, when I say how resistant, that's not just only about economic losses, that's what we usually use money to refer the risk eventually, the money losses or possible cost of economic, but also about fatality rate and also even well-being. Well-being means that whether your behavior will change before and after storms. Where you still, before the storms, you buy one coffee from outside per day, after storm, will you still doing the same, or you will start to thinking, oh, I need to actually step back on my coffee expense, those kind of things. Yeah.
Yeah, this actually relates to a question in the chat that Stephen Mack asked, having to do with some of his work, anthropological work, showing that there are changes in we'll call it urbanization, or basically human development, that increase risk factors. But the issue here, when you divide risk into the probability of a hazardous event, the exposure of people and properties and livelihoods to that event, and in a civil engineering term, the fragility of that, right? It's important to probably think about what we can contribute in a very quantitative way to any of that, and how we interact with other fields or other data to figure that out. So in getting back to the Columbia risk model, can that be used, say, with social scientists or with economists to try to figure out what the risk, what is the decision ethic that's going to come out of the use of the Columbia hazard model?
It is actually, it definitely can be used. So Columbia hazard model itself is generate. So, okay, so let's just say, take a step back, how in the industrial, how we define the risk, right? So in the industrial, when insurance company, they are talking about risk, they are actually get information from so-called catastrophe model. Catastrophe model is a model that generates synthetic events. So they are usually just looking at the past data and try to use that past data as a model event and perturb a little bit. In the hurricane case, they probably shift the track a little bit towards north, toward south, and generate a bunch of synthetic events called daughters events, and using those data to generate probability. The problem with this is they heavily rely on past data, and that on the assumption that the climate is stable. The Columbia hazard model, on the other hand, it generates those daughter event or synthetic data by taking information from climate model. And then we can actually provide those synthetic data to the social scientists, to people who are using to connect with social scientist models and to therefore to use. And in fact, it has already been using it. One of our project is using those models to generate probability of event, to generate a synthetic event, to estimate the damage hurricane will causing on the oil tank in the Houston ship channel. And then based on the damage caused on the oil tank, we're looking into the health risk of the Houston ship channel communities there. So this can be used, but it has to through the collaborative work between us, social science, and sometimes even civil engineer has to be involved.
Yeah, this has been, I mean, the notion of risk and the role that, say, insurance plays, but the way in which the work that we do as physical scientists can be used by others who understand or work on the fragility or the vulnerability of society, something that has been very important, I think, in some of the work that we do. We certainly see it in earthquake risk, for example, and that's sure, which is also an issue. But Michela, when you've worked, say, in the Sahel, and trying to understand the notion of drought versus extreme rainfall, how has that information been used, say, by, say, the World Food Program or the development community? Have you seen any utility coming out of the work that you do?
Africa is a place that has maybe not the same infrastructure for dealing with risk as the US has, but one of our graduate, Usman Jai, he's now, was the head of the Met Service in Senegal, and is now the director of a Africa-wide agency that is meant to help weather agencies deal with climate as well. And so, you know, it's a long path to be used, but it can be used, right? So the idea of understanding how the rainy season can be wetter or drier or delayed, right? And then communicating that to farmer is something where you need somebody to, who has seen this done, for example, here, to then go and take that information and figure out how to package it for the population there. So what Usman has done, for example, has been to package the climate information together with agricultural information, and going both from the weather scale, like don't put fertilizer today because it's going to be washed out, right? Wait, to the climate scale. We think that this is going to be a dry year. Plant these seeds, not those seeds. But again, there needs to be a strong connection with people on the ground who can translate that scientific information into actionable suggestion, and then get that suggestion in the right hands in the right way. But it is very heartening to see that this work is done, is getting done. Maybe more patchwork than we would like. It's not continent-wide, but there's progress there.
Both of you, that's good to hear, but let's turn to how we're dealing with our students these days. Both of you have been teaching and interacting with students for your careers, as have I. So I've certainly seen changes in the way our graduate students are approaching their theses and what they want to do afterwards. Michela, what's motivating the students that you interact with these days?
I think there's still quite a lot of scientific curiosity. Just the fact that we have an interesting question that needs to be answered. It's good when you have an itch and you can scratch it. And still, so we love the science because it's fascinating. At the same time, I think everybody who's coming into this field is also very much aware of the fact that climate is changing, and we are not responding to that change in the way that we would that we think we must. So I think there's that in the back of their mind, and they are activists and they are concerned citizens, but I think they can still work on the atmosphere because it's just the coolest place ever.
Science lives, yes. Yeah, Chia-Ying, you've, in addition to your work at Lamont with graduate students and all, you're also teaching in one of our master's programs, the Sustainability Science program. What's the approach of students there, and how do you deal with them? Or what are you seeing there, their motivations?
I think the student there is more like they are trying to seek for information or knowledge that can help them to deal with the climate impact in their life, in their work, or in things. Or there's one student I remember very vividly is she experienced the Brazil flood. And then that kind of totally changed her life. And she decided she wants to work on a job that will be able to mitigate or adapt her countries, will help her country to do the flood mitigation and adaptation. And that's what motivates her to join our program, because she really want to know what's the basic concept of what causing the flood, and knowing what's the events, what's the projection, and then discuss with us of what we think of with other professors as well, is how can she equip herself well into the field that working on flood mitigation. So I think for the master programs, the motivation is really kind of what Michela is saying, is that we know the climate changing, but we are not doing well enough. And how can I do better? How can I equip myself enough knowledge and skill in order to step in the field, either to become translators between the science and the practitioner, or working directly as practitioner.
All right. Well, the School of Professional Studies is an interesting school. That's another topic for another day. We can get to that later. But it's interesting to see how the work that we're doing at Lamont, the fundamental research that we hope will continue to be supported, of course, is also being used in a very applied way, not just by our students in the master's programs, but also by the insurance markets, by economists, by social scientists, and others. It's really enlarging the impact, our footprint, as it were, on society. Let me end by talking with Michela and Chia-Ying about, say, the obvious difficulties that we're facing on the research front with respect to the federal funding of climate research, as well as the importance of the ongoing data collection and data aggregation efforts that have actually been interrupted in some way. Michela, what are you seeing in terms of the databases that are necessary for the work that you do, their continuity and their sustainability? What are you worried about these days?
Well, climate, right, has been piggybacking on weather for the most part. So already we didn't really fund a climate observing system the way we've been finding a weather observing system. And what I mean by that is that we haven't been as careful in trying to keep that continuity, that ability to know, to monitor trends in a way that we are sure they're real trends and not trends in the observing system. The buoys that have helped us understand and predict El Niños, those are expensive. They already were under attack. And now we see the two things happening that are worrisome. One is the the announcement that some of these important satellites are not going to be supported, right? That give us really good information about, the energy input and output into the atmosphere, the CO2 measurements, the water vapor measurements that are key to a lot of our work. And the other thing that is absolutely crucial, not just for US science, but really for the world's science, is the fact that the US has been a really important provider of free data, easily searchable, easily accessible, for a long time. And it would take quite an effort for others to pick up the slack. First of all, make sure that the data is available, and there are nonprofit efforts happening right now, but it's disturbing.
It is disturbing. And one of the aspects of this, I think it's important to reflect. I'm sure our participants know this, of course. You don't turn science on and off. And let me conclude with just a few thoughts on this and the relationship to our 75th anniversary. As we concluded our 75th anniversary year last June, Columbia was, of course, facing stress, as it were. I mean, to put it mildly. And one of the things that a bunch of us noted in the work that was being done at Lamont is that the science thinking never stopped. People were still practicing science, were still doing science. Our students were still enthusiastic. Our scientists were still enthusiastic. And when you get right down to it, that continuity is really important. The the volatility, if you will, in the funding that's happening right now is something that we have to deal with. And we hope that this series and what we're going to be doing in the future will motivate our friends to help us get through this period of uncertainty. So the trend line has always been good. The volatility is extreme right now. The public supports science. We want to continue to doing the science. We actually need your help. And so let me remind everyone that Columbia's annual Giving Day is October 21st. We will continue these discussions, conversations with Lamont scientists in December. That will be our next one. And I do want to close by thanking Chia-Ying and Michela, not only for their scientific comments at the opening, but also their questions and discussions following. I didn't get to all of the questions in the chat or in the Q&A. I apologize for that, but I hope that we covered in general the topics that you've been interested in. As always, please keep coming back to us and help us get through this period. But ultimately, we enjoy talking with you and we enjoy doing the science that we do, and that's going to keep us going. So thank you all and take care until December. We adjourn.